Dear delegates, Caspian Sea is highly sensitive to a varying climate. And although past IPCC reports have not specifically assessed Caspian Sea, we know from its global assessment that as global temperatures rise, increased evaporation rates are expected to lead to significant declines in water levels, altering ecosystem and leading to severe socioeconomic consequences for the surrounding regions. In this presentation, I will present a high-level overview of the water-related impacts of climate change and possible implications for the Caspian Sea. We know from past IPCC assessment that climate change impacts present overlapping challenges. Climate change combines with unsustainable use of natural resources, habitat destruction, deforestation, growing urbanization, as well as inequity and marginalization. And these trends not only present threats to ecosystem and the people who rely on them, such as those around the Caspian Sea, but also reduce the capabilities of nature, communities, individuals to adapt to climate change. Impacts are magnified in cities where over half the world's population lives. Heat waves amplify urban heat islands, air pollution affects people's health, critical infrastructure such as transport, water, sanitation, energy systems have been compromised by extreme events that have resulted in increased losses and damages. The climate change impacts are severe in vulnerable regions where the capacity and resources to respond are limited. And we see in this figure a global map of vulnerability and examples of local vulnerable populations that live in highly vulnerable countries. The hotspots are across large parts of Africa, South Asia, Central and South America, small islands and the Arctic. About 3.3 to 3.6 billion people live in global hotspots of high vulnerability to climate change. In these global hotspots, overlapping challenges include limited access to water, sanitation, food, health service, high levels of reliance on climate-sensitive livelihoods, such as smallholder farmers, fishing communities in these regions, will all increase vulnerability. Looking to the future, every small increase in warming will result in increased risks to nature and to people in every region of the world. When multiple extreme events happen at the same time, they compound to the overall risk, and they are even more difficult to manage. What we see here is an example of how heat and drought combine to cause reductions in crop yields, made worse by reduced productivity because of heat stress among farm workers. Reduced yields lead to reductions in household incomes, increased food prices locally and potentially even globally. Climate risks do not respect national boundaries, and weather-related extremes are creating shocks to global trade. Water security is central to responses to climate change because of several reasons. For instance, 4 billion people are currently subjected to severe water scarcity for at least 1 month a year. Climatic and non-climatic factors contribute to water insecurity. Factors as drought or pollution, resulting in too little water, and extreme precipitation or flooding, leading to much water, they are all affected by climate change. The social factors can serve as barriers to water access or protection from water-related damages. At approximately 2 degrees of global warming, between 0.9 and 3.9 billion people are projected to be increasingly exposed to water stress, depending on the regional patterns of climate change, of course, and on socioeconomic scenarios considered. With agricultural and irrigation accounting for 60 to 70% of total water withdrawals, and 10% of the most water-stressed basins producing 1/3 of the world's irrigated calories, food production in these basins and consequently globally are at risk. Almost 2/3 of all adaptation responses documented since 2014 are in response to water-related hazards like drought, floods, rainfall variability. Water-related adaptation action features predominantly in nationally determined contribution pledges by most countries, both in the global north and in the global south. Critically, most of these water-related adaptations are more effective at lower global warming. It really stresses the importance of mitigation efforts to ensure future adaptation actions remain effective. And while limiting global warming to 1.5 degrees would minimize the increase in risk by the various water use sectors, and it would ensure adaptation to remain effective, many mitigation measures in themselves can potentially also impact future water security. For example, bioenergy with carbon capture and storage, afforestation, reforestation, they can have considerable water footprints if implemented in inappropriate locations. It's therefore crucial that a full systems approach, considering the direct and indirect impacts of mitigation measures on water resources, is taken to minimize the risk to water security. All components of the water cycle have been affected by climate change in recent decades, with hundreds of millions of people now regularly experiencing novel hydrological conditions. Precipitation patterns have shifted in three main ways. Some regions are experiencing more annual or seasonal precipitation, while others receive less. In other words, changes in longer-term average precipitation levels occur. Many regions are seeing changes in precipitation extremes, which manifest either as increased heavy precipitation or increases or decreases in dry spells, independent of the annual precipitation trend. And some regions have experienced shifts towards heavier precipitation events separated by longer dry spells. The second element is evaporation. Evapotranspiration has changed in response to changes in precipitation and temperature, resulting in changes to soil moisture levels worldwide that are now detectable by satellites. The global cryosphere has been extensively impacted by rising temperatures, with mountain glaciers, land ice, snow cover shrinking, leading to permanent changes to the ways of life of people in regions fed by cryospheric water supplies. Groundwater recharge in spring may have been reduced, however, non-climatic drivers like increased abstraction or irrigation, they are the dominant drivers for reductions in groundwater reserves. Streamflow patterns have changed globally in response to the changing climate. Extreme hydrometeorological events, including heavy precipitation, flooding, drought, wildfire events, they have been shown to be made more likely by anthropogenic climate change. Annual mean precipitation is increasing in many regions of the world, particularly in the mid to high latitudes, and decreasing over a smaller area, mainly in the tropics. More people live in areas where short-term precipitation extremes have increased than in areas where these extremes have decreased. More people are experiencing longer dry spells than shorter dry spells. Global mean soil moisture has slightly decreased, but regional changes vary widely, with 20% or greater increases or decreases, depending on the region. The resulting droughts and floods have substantial economic and social costs. Many other water-related indices have changed over the last few decades, but the impact of climate change is difficult to differentiate from the impact of changing use. For instance, the effect of increasing irrigation intensity on groundwater, or land use change effects on the sediment load of waterways. Other indices exhibited localized changes which may not be discernible at a global or even regional scale, and often aren't sufficiently documented in literature. We've seen multiple ways that climate change impacts the sector and how these cascade to various aspects of human and natural systems. And we also know that there are principles that can enable water security and climate resilient development. For instance, technologies that reduce carbon emissions by promoting efficient use of water that can support a successful adaptation. These may include irrigation methods that minimize water wastage, like drip irrigation, wastewater recovery technologies that allow water to be reused, as well as use of solar power for irrigation, wastewater recovery, desalination, water harvesting. However, technology can be expensive and needs to be appropriate for the local context. Adequate and appropriate financing is also essential. A substantial portion of adaptation finance currently goes to the water sector. with urban areas tending to spend most of their adaptation budget on water and wastewater management projects and disaster risk management. Cuts in adaptation financing because of the global pandemic may impair developing countries' ability to invest in adequate water-related adaptation. Equity and justice are central to climate change adaptation and sustainable development, as the world's poorest and most vulnerable people and countries are impacted by the changing climate and are least able to access adaptation strategies. And this definitely also applies to the water-related impacts of climate change. Indigenous knowledge, local knowledge, are dynamic and have developed over time to adapt to climate and environmental change in culturally specific and place-based ways. Ethical co-production of knowledge is a key enabling condition for successful adaptation strategies pertaining to water security, as well as in other areas. It's also critical for the development of effective, equitable, and meaningful strategies for addressing water-related impacts of global warming. Participation, cooperation, bottom-up engagement are critical for optimal adaptation, considering that many of the countries and social groups that are most threatened by climate change have contributed the least to global emissions and do not have the resources they need to adapt. Supportive legal, regulatory, institutional frameworks for effective stakeholder participation are required for an inclusive water governance. Also, incentives for bottom-up and participative decision-making in the water sector can facilitate effective stakeholder management, which in turn helps build public confidence and trust in water governance. Polycentric governance, in other words, governance without a central authority, can encourage and support participatory, decentralized, deliberative adaptation, which in turn can produce better environmental and water governance outcomes, provided that there is the perception of fairness and inclusivity in the decision-making process. And it can also be an effective enabler for adaptation when it connects multiple public and private actors across different sectors and scales to come up with coordinated water adaptation measures. And finally, without strong political support or the collective willingness to act, together with economic, institutional, developmental support, climate change adaptation processes are quite unlikely to be effective. International donors, transnational legislation can support the capacity of national and subnational governments to act and remove barriers to the effective implementation of adaptation policies in the water sector.